now what I'm going to cover is SNCC. It is simple non-iterative clustering, wherein we have shifted our gears from supervised learning to clustering. So clustering has its all importance in several domains, which I'll be covering one by one to you. Before that, just to give you a brief of what all topics we have covered in all the 9 segments that we have covered in the webinar are the following. It is we had a touch with the functional programming. We have learned how to import different things like images or geometries in Google Earth Engine. We have learned supervised classification. We have learned the charts. We have also have our glimpse on linear regression. We have seen the exports, some thoughts on radar imagery and wheat crop classification, and then the last segment was about the band match, wherein we saw what all how we can calculate, how we can make use of different bands of satellite images, and we can derive different results out of it, different indexes out of it. So today the part is about clustering, which is not a classification basis. Actually, it is also it can also be treated as unsupervised classification, wherein you are not giving any parameter to be learned. You are just saying the model to learn on their own and then create clusters out of it. So now we have moved up from pixel level classification to object level classification. So SNCC almost deals with that, wherein we create objects and we give some properties to it, and then we can use those objects for other different studies that we are doing. So in this case, we have a Landsat 8 RGB image. This is a seeded image. The code and all I'll be sharing with you, and will be explaining it thoroughly to you. But before that, let us first understand what is this. So this was the actual RGB Landsat 8 image, wherein we have seeded the image. Seeding the image, it means that we are randomly putting some points which are at equal distance to each other. We are putting the seeds or the points on the image, so that this point will be considered to see the neighborhoods and in the creation of the objects out of it. So you'll see it later on. Next, we create some clusters which are individual objects. Now there are different benefits of creating objects than performing your classification on pixel based scenarios. So in objects, you have a specific property out of it. You can derive whatever you want, like you can relate two different objects, you can calculate their standard deviations, you can give their area, you can derive their parameters, or these all things. So wherein it is extremely important or extremely beneficial in the case of precise agricultural field monitoring, where you have a very high resolution data set and you want to precisely monitor your field, a single field. So you can create an object of that field, and you can relate it with other different parameters that you want to do. So with this, what we do is we use reduce connected components function. Why so is the following reason: because each and every cluster here is an object. So object has all these pixels connected to each other. So that is why we say we'll use reduce connected component function to see or to derive some results out of it. So you can create the area, or you can derive the deviation of one object to another object, and you can relate it likewise. So with this, I'll be showcasing you the implementation or the code, a simple code to make you understand how the things go well. So validating it with Jyoti, my screen is visible, right? You can see the
Yes,
code.
yes, definitely.
Great. So yeah, so we have chosen this particular Landsat 8 image, where we are selecting RGB bands. That's all. We are sorting it out for the land cover, for the cloud cover, and we are seeding the image. So this is the function that is used to generate the seeds. Here in this particular image, you can see the seeds. I hope it is visible.
Yeah, it is Guneet. It's visible.
Yeah, nice. So these are all white colored dots on the map. Just give me a second. I'll make it red so that it will be more visible. And
Hmm.
So this was the RGB image that we took, though it has much more cloud cover. So in practice uh, we should try to remove all these clouds, or we should select a better image out of it. So just for a demo purpose we can consider this image, because we are understanding how this snake works and what are the benefits of it. So we are considering this small image out of it. And yeah, allow it to load for a minute. So this seed grid function inside segmentation module will generate the seeds out of it, and these seeds will be visible to you in a minute or so, because it is still coming up on the map. Yeah, so all these red color dots, these are known as seeds, wherein they are equidistant from each other, and these all will be the base points for your cluster mechanism. So this point, one point will be considered, and its relative neighborhoods will be checked. So the problem where comes is, so this seeds has resolved the problem of choosing which pixel should be considered as the base and which other pixel should be considered as the derived uh, pixels, so that we can create a cluster out of it. So now these seeds are the base for it. So first these seeds will be considered, and all the neighborhood pixels, which we will only give how many neighborhood pixels we need to consider, checking the similar properties, it will create the clusters out of it. So you can implement SNCC algorithm with this particular already implemented algorithm, which expects you to give image on which you want to apply the SNCC algorithm, then compactness, connectivity, and neighborhood size. These three things are the most important one, which are necessary to be given. So compactness tells how compact your particular cluster will be, means how much tightly it will be coupled with the. So connectivity tells how many pixels it need to consider nearby, means it should be considered with let's say you are making a polygon. So a square is also a polygon, a rectangle is also a polygon, then a pentagon is also a polygon. So this connectivity tells how many pixels will be connected at the edges. So if you are saying it 8, so 8 means what? It will be octagon. The clusters will be in the form of octagon. So the borders should be connected with 8 different pixels. So 8 pixels will derive the border of that cluster. So this is connectivity. Neighborhood size means how many neighbors should be considered. So I mentioned like 60. So with this, each single seed, 60 neighborhood pixels will be checked for the similar properties. If they hold the similar properties, then they will club together in a single cluster and will be formed an object. This is how it works. So we are passing the seeds. Seeds are the base for checking. Now each seed inside the image will be checked for 60 neighborhood pixels, and if they hold a similar kind of property, they will be clubbed together to form a single object. So after passing all these things, we are using this SNCC. We are adding it up using random visualization onto the map, which you can see here. So yeah, these are the clusters that are coming up on your screen right now. Yeah, so I remove the seeds layer. So these are the clusters basically. The compactness, connectivity, and the neighborhood size will determine how your clusters will look like. If you'll say connectivity to be 4, so each of your clusters will look like squares or rectangles in shape. If you are saying it 8, it will try to be an octagon. Likewise, if you say your neighborhood size will be 60, so 60 different pixels nearby each seed will be considered to form the object out of it. So by the time it loads, we have a playground. Just wait a minute, it is loaded. So these are all the clusters that have formed up. So it is important to note that each of these cluster is a different object that holds a different property. than any other object out of it. Now we can take these clusters to enhance our experience, or enhance our experiments that we are performing. So we have this playground thing available with us, wherein by changing the parameters like compactness, connectivity, and the neighborhood side, we can see how the things work, how the things changes. So this will uh, this will uh, this will be like more visual uh, experience that you will be getting after changing all these things. So you can see how these things affect, these parameters, compactness, connectivity, affect the total cluster formation. Let's say I change the compactness to 5. Now if I'll change it, you'll see the results over here in the left hand side. Can you see the difference? So by default, this is the default parameters that we have chosen. Now here in this particular cluster has a irregular shape after using the compactness. So there are two uh, different clusters that are formed here with a defined shape. So it limits the cluster formation. It will stop them from expanding too much in some irregular direction. So connectivity, let's say I'm reducing it to 4. So now each seed is connected with 4 different pixels around. So just have a look at this particular cluster, wherein you can see it has a big size by default, but if I changed this connectivity with 4, though its size and the properties are reduced, it is just half of it. So that is what we did. We made the connectivity from 8 to 4, and this is how the shapes are changed. See, before in this particular area, earlier only 2 clusters were formed. This is this one and this other one. Now there are 3 clusters, because we have said that it should be connected with only 4 pixels at the corner, at the edges. So I hope that made you it gave you a simple glimpse of how we can make use of clusters, how we can apply SNCC algorithm on Google Earth Engine. So in terms of benefits, as I earlier told, now these all are different objects. You can assign the area to them. You can see, you can derive parameter of each of the object. You can do precise calculations, precise modification, precise experiments for a single object that you are interested in. It is best when we have very high resolution satellite imagery available, like NAPE, which is a free imagery program from US. So it has 1 meter resolution imagery, so you can apply on it, and each single field, like this is one field, can be can be used to do a precise calculation on it, or a precise work that you want to do as a single object. Now it is not a pixel, it is a single object, and you can do all other calculations that you want to do. So yeah, with this we have shifted our gaze from from pixel level classification or pixel level work to object level work now with this SNCC. So with this I would like to get back to the call. Yeah, so yes, with this we have almost covered all the things that we would like to cover today. So we will be sharing with you the whole script. The video will be available online to you on the YouTube channel that we have, EE India Community, and from there we can learn together. And if you have any doubts, you can anytime mail any of us, Jyoti or I. So we'll be answering your questions, we'll be looking deeper into your questions, and we'll be resolving it out, right?